Welcome back, everybody. So now that we've done an overview of solving the Schrodinger equation and quantum mechanical problems for simple, what we might call toy problems, and then we've looked at the actual crystal structure of materials like silicon and other semiconductors, we want to put those two things together now. So what we're going to look at today is electrons in periodic potentials. And what we can think about is starting with a 1D problem to sort of get the essential physics. So we might have what we would call a chain of atoms where they're all separated by a certain distance, A. And what we want to think about is what the wave functions actually do in this periodic potential. So the easiest way to visualize this is to consider first a chain of hydrogen atoms. So on this slide, we can see the Coulomb potential presented by a single hydrogen nucleus, and then by two hydrogen nuclei next to each other in a hydrogen molecule. So if we look at just these two atoms, we have these potentials added together. Here's our energy. And this shape here is the total V as a function of x. And our wave functions are going to look something like the wave functions for the original hydrogen atom. So I'll draw the wave functions in red here schematically. So the overall wave function can be thought of as the sum of the wave functions having to do with the original atom. And it turns out, though, that we have two solutions because we're sort of adding together the wave functions from two atoms. So we could call this the E plus solution. And then we can draw another solution where instead of adding these two things with a positive sign, we might add them with a minus sign. So this one would be like psi 1 plus psi 2, and this one is psi 1 minus psi 2. And what happens is that the energies of these two levels, if before we had the E for the hydrogen atom, these two E plus and E minus actually go slightly up and slightly down. Oops, E plus. And so we call this the splitting. Okay, so let's look back now at the PowerPoint and see what would happen if we had a chain of atoms. So if we had a very long chain of these hydrogen atoms, we can see that it looks like the case for the two hydrogen atoms, except that we're adding more and more of them together. And what happens, because we have, let's say, a large number n atoms, we're also going to have n solutions to the Schrodinger equation, each with slightly different energy. And then each of those solutions is going to split just a little bit away from the original energy that we started with. And so instead of a single energy level, or even two for two atoms, we're going to have n energy levels that are split by very small increments of energy into what we'll call a band of states. So we want to look at the mathematics of this a little more closely and actually solve another toy problem, except this one is actually more complicated. It's a very advanced toy, let's say. But it does give you the essential physics that you'll get bands of states separated by band gaps. So this model is called the Kronig-Penney model. We're going to work on solving the Schrodinger equation in a periodic potential. And instead of solving the actual problem, including the details of the Coulomb potentials, we're going to turn those Coulomb potentials into a more convenient rectangular shape, and then look at the solutions. And what's nice is that the essential physics of bands of states separated by band gaps comes out of this model. So we're going to represent the potential of a chain of atoms by regions with potential equals 0, separated by regions where the potential has value V naught. And at each of these atoms, the potential really diverges to negative infinity. But instead of that, we're going to set our 0 down at negative infinity and make the height of these our V naught and set our 0 there. So our energy comes up like this. So our potential then is rectangular, and we know how to solve problems like this from the previous problems of electrons in a finite square well and electrons in free space where V equals 0. And then also in between the atoms, we're going to represent the solutions as tunneling problems. Okay. So the first thing we have to do, it turns out, when you're dealing with a periodic potential is to represent your solutions in the block form. And the block form is shown here on this slide. And it's essentially a plane wave, which is then modulated by a function which is periodic with the same periodicity of the potential. So we're going to seek solutions in this potential where we can have plane waves, which would be our normal e to the I kx type, and they could have different wavelengths. But they're going to be modulated because of their interactions with these atoms. They'll have little wiggles. But the nice thing is that these little wiggles have to have the same periodicity of the lattice. So that gives us the property that u of k and distance r has to equal u of k and r plus the repeat period a. So this allows us to solve the Schrödinger equation only in one of these repeat units and then know the full solution over the entire problem. So what we do is we plug in this guess for the wave function, which includes both the plane wave part as well as the block function part, this u. And we end up with an equation for a Schrödinger equation for the u of r itself. And then we can go and solve that. So in the two distinct regions, the tunneling region, we're going to use a constant beta instead of our normal k. And in the region in between the tunneling barriers, or one could look at it as the region in which the electron is sitting in a finite square well here, we're going to use the propagation constant alpha. So the model can be parameterized with this A and B for the thicknesses of the well and the barrier itself. On this slide, the notation differs a little bit from that in the book in that A is the actual repeat unit distance and that matches with this definition here of the block functions. Okay, and then our propagation constants, alpha and beta, are defined here. They look exactly like the k's for the free particles or the tunneling particle, and in terms of having some energy term in the numerator, and then the energy minus the potential in the numerator for the beta. So in the end, we end up with this large transcendental equation, which if we solve this equation, we will have solutions to the Schrodinger equation for the u sub k of x. I'll illustrate now the procedure that we just went through. So we can write our Schrodinger equation as h psi equals e psi. And we plugged in the block solution. So we plugged in our guess that psi equals u of k. And I'm going to switch to x because we're doing a one-dimensional problem, times e to the I kx. So we're going to find that for each value of k, which means each wavelength of the traveling wave through this periodic potential, we're going to need to have a different u of k and x here. And when we plug this guess into this function, we end up with some expression. So essentially a Schrodinger equation for the u of k and x itself. Okay. And now what we're going to do is actually, once you have this equation, you can find solutions for the equation only under certain conditions. And those certain conditions are spelled out in the book, where you end up taking the determinant of a certain matrix and finding where it's equal to 0. And that gives you this overall master equation, which essentially says the cosine of k times a plus b equals some big function which involves alpha and beta. And these alpha and beta, remember, are the propagation constants that are both functions of energy, and also the v naught. Okay. So what this master equation says is that we can find solutions to the original Schrodinger equation if we can match up the left-hand side and the right-hand side here. So now let's look at this function in a schematic first, and then we'll look at the actual plot next. So we have the left-hand side and the right-hand side. Some big function here of alpha and beta, and it turns out A and B also. So what I'm going to draw is schematically the right-hand side of this equation. So that will go in green, I guess. And this looks like a damped oscillation. So this is the Now if we look at this left-hand side, the key insight is that since it's a cosine function, it has to exist only between these plus and minus 1 limits. So without looking at the exact solution, we can already see that these regions out here cannot satisfy the master equation, and thus can't be solutions for the Schrodinger equation. So what we're left with are regions here where solutions can exist. Okay, so let's look more exactly at these solutions. So here I've actually plotted the function in terms of energy measured in joules, and the function values on the y-axis, and you see these regions in blue where bands of solutions exist. So in terms of increasing energy, we start with a band gap where no solutions can exist, followed by a band of solutions, which are just like the ones that I talked about at the beginning of this section, where these energy levels split and form a continuous band of allowed states. And then another gap, another band, another gap, another band. So if we actually go back and look for the real solutions, so now we're going to actually solve for k here and take the arc cosine of both sides and move the a plus b over here so that we're left with k isolated. We get this plot here. And again, we have the structure of bands of allowed solutions separated by gaps where no solutions exist. But if we look at the actual energy as a function of k, we get the actual relationship between the particle's energy and its momentum, since the momentum is proportional to the k values. So what we just did was actually solve the right-hand side and left-hand side for the value k. And so we're sort of doing things backwards compared to what we usually do, because usually we plot the independent variable on the x-axis and the dependent variable on the y-axis. But we've sort of reversed things when we're solving. We're looking for the values of the x-axis which match with values of the y-axis. Any way you cut it, though, what happens is you get these bands of solutions that exist something like this. So there's a limit to how far out in k the solutions can go. Because we were working with a cosine function, it turns out that solutions can only exist between plus and minus pi over a. And I'm only drawing 1/2 of that right here. So here's our band gap, and here's our band of solutions. And you have to remember that this is actually a discrete band of solutions. Each atom in the crystal adds one solution to this band. So we have to take this k not as a continuous variable, but quasi-continuous, because it's discrete but a very large number. And so there's actually finite k values, each one having its own energy. So this function is a little more complicated than we want to deal with. And it turns out that usually all of the actions in the semiconductor will happen right near either the top energy or the bottom energy within a band. So what we end up doing is really only worrying about the first part of this function, which is near a minimum, and we're going to approximate that by a parabola. And the parabola is used because it represents the kinetic energy of a free particle very well. And so we can treat the electrons or the holes in the semiconductor as if they were free particles, as long as we take into account the details of this parabolic approximation to the real E versus K relation. So the equation for this parabola is going to be h bar squared k squared over 2 times the mass, but now it's not the true electron mass, but rather what we call an effective mass. And the effective mass essentially just matches the curvature of this real EK relation to this parabola. So we can see on this slide that a true parabola could represent a particle such as an electron in free space, and we saw that from the free electron problem for the Schrodinger equation. It could also represent things like baseballs and other classical objects. So in the next short video segment, we'll look at what this E versus K diagram actually means in terms of wave propagation. We're going to go back to our guesses for the solutions to the Schrodinger equation, and remember that they're representing traveling waves in the crystal. And so we're going to revisit a little bit of wave mechanics and see how this EK diagram relates to how the waves actually move.